Hi students, today we are going to discuss about the solubility of liquids in liquids. That means one solvent in another solvent, one liquid in another liquid. How about the solubility? How about that mixing ratio? How about that mixing component, whether it is completely mixed or partially mixed or it is completely not mixed each other. It means miscibility. One on another is miscible each other or not. That is miscibility. That is partial miscible, completely miscible, completely immiscible. Right? These are the three important phenomena which we are going to discuss in liquids and liquids, and also we are going to discuss about the applications of liquids in liquids. Okay, how the classification occurs? Okay, I said the three classification. The first one is completely miscible liquid system. If I take two liquid system, for example water and milk, right? This is we are seeing in our regular life. Water we are adding into the milk. What will happen? This is mixed each other and it will produce the homogeneous solution. That is mean completely miscible. If we take the second part, partially miscible liquid system. So here that means if I add the liquid A and liquid B, that will produce partially miscible, that is not miscible completely. That is the name is called partially miscible liquid system. The third one is immiscible liquid system. That means the two liquids are not at all miscible. So for example, if I take organic and aqueous layer, organic solvent example, we can say what is it? We can say acetone or any of the methanol or benzene, for example. Okay, organic solvent. If I take particularly organic solvent like carbon tetrachloride is the organic solvent, right? That is example of non-polar solvent. That is the dipole moment is 0, right? So from the previous lecture we have seen that already. Okay, the carbon tetrachloride if I add with water, what will happen? That is not miscible each other. That is not completely miscible, right? So that is the example for immiscible liquid system. Carbon tetrachloride and water. Okay, we will look into that the more detail about completely miscible liquid system. When both the liquid components are mixed in all proportions, then called as completely miscible. If I take 1% and 99%, if I take 95%, 5% of the component A or liquid A and liquid B, if I mix, definitely it will be mixed completely. Any ratio 50-50, 40-60, any ratio if I take, that will be completely miscible. That is called the completely miscible liquid system, or that is called binary systems. Okay, binary means two liquids completely miscible. That is called binary system. Okay, here we can take that one example. Polar and semi-polar shows complete miscibility, right? If I take water and mix with ethanol or methanol, that will what will happen? Completely form the single solution, right? That is completely miscibility is happening. Then the second one is non-polar solvents show complete miscibility. Non-polar solvents, for example benzene and carbon tetrachloride, that is miscibility is possible, complete miscible. Okay, these are the concepts liquids and liquids explained by Raoult's law. Okay, in the previous case we have explained the gases in liquids, explained particularly for the pressure effect by Henry's law. Here liquids and liquids, the solubility explained by Raoult's law. Okay, what is Raoult's law? So any given temperature and pressure, the partial vapor pressure of any component of a solution is equal to its mole fraction of the component A multiplied by vapor pressure of the component in the pure state. How can we mathematically express this one? PA. What is PA? That is the partial vapor pressure of the given component. And what is XA? That is the mole fraction of component A, and PA0 is the vapor pressure of this component. Okay, so here PA is equal to, PA is partial vapor pressure is equal to PA naught, that is the vapor pressure and multiplied by mole fraction. Okay, partial vapor pressure is equal to vapor pressure into mole fraction of the component is nothing but Raoult's law. Okay, so Raoult's law have some limitations. What are they? This is able to apply only to dilute solutions. It will not be applicable for concentrated solutions. For example, concentrated hydrochloric acid, if you ask Raoult's law, though it will not give any kind of answer. So it is failed to apply for concentrated, is only applicable to dilute solutions, and this applicable to solutions containing non-volatile solid. Okay, that is the boiling point is high wherever it is, then that particular liquid only this Raoult's law will be applicable. The third one is this not applicable to solids which dissociate or associate in the particular solution. If any electrolytes if you take, that we cannot use this Raoult's law for the to know about the solubility. Okay, the solubility of liquids in liquids. So the next concept in this particular topic is ideal solution. What is ideal solution? The solution in which the properties of the individual components do not alter upon the dilution are known as ideal solution. If you take the two mixtures A and B, if we mix it in the different volumes, and it will produce the component C, that is A plus B, that volume of both the individual and overall is equal. That is called ideal solution in the given temperature and pressure. Okay, ideal solutions are obtained by mixing the substances with similar properties. We should not mix the non-similar properties. Only similar properties of the compounds we can mix it, and we can get the same amount of volume. Then we can just say that this is the ideal solution. Okay, solutions which obey Raoult's law, that is very important component for the ideal solution. If you want to, solution should be ideal. If I say the solution is ideal solution, this ideal solution should obey the Raoult's law, that is PA is equal to XA into PA naught. That Raoult's law should be applicable or obeyed by this the solution, given solution. Okay, that is the Raoult's law at every range of concentration and at all temperature and pressure, or should be behave as ideal solution. So we can obtain ideal solutions by mixing two ideal components, that are solute and a solvent, having similar molecular size and also at the same time similar properties and similar structure. So we can say that is the ideal solution. For example, consider two liquids A and B. I am just mixing each other. So here AA intermolecular forces of attraction. So B is the possibility of intermolecular forces of attraction. Another possibility of attraction is A and B. Okay. So the formed solution will experience several intermolecular forces, right? These are the above mentioned intermolecular forces. So solution is said to be an ideal solution only when the intermolecular forces of attraction between AA, BB and AB are, what will happen? Nearly equal. So AA should be equal to BB, BB should be equal to AB. The force of intermolecular attraction should be equal in all the three categories. Then we can say this solution is ideal solution, and similar property should be maintained. The interaction should be maintained ideally, and also it should be in the given temperature and pressure, and a similar molecular size and structure. These are the properties we need to maintain for the ideal solution. Okay, so ideal solutions are obtained by mixing substances with similar properties, as we seen in the previous slide. So example, methanol and water. Okay, so this dielectric constant for both is more, that are also coming under the polar protic solvents. So we can give the example, we can just add methanol and water. The second example, benzene and toluene, the same way N-hexane and N-heptane solutions mixed, that is coming under the example for ideal solution. Next, properties of ideal solution. What are the properties, right? The first one is it should obey Raoult's law. The second one is heat is neither evolved nor absorbed. If it is evolved, what is the name? Yes, exothermic process. If it is accept or absorb the heat, what is the process name? endothermic process. So either exothermic or endothermic, that process, that both can be heat is neither evolved nor absorbed during mixing process. They should not be evolved or absorbed. There is no exothermic process and there is no endothermic process. That is, heat of solution is equal to heat of fusion. The point number 2 is the properties of ideal solution is heat is neither evolved not absorbed during the mixing process. That is, heat of solution is equal to heat of fusion. Heat of solution is equal, that means dissociation is equal to heat of fusion. The third one is the volume of mixing is also 0. If we just add the delta V mix A and B, I am mixing, the total volume mixture is equal to 0. The fourth one is the forces between the like molecules are same as those between unlike molecules. So whatever it is like molecule or unlike molecule, the forces, intermolecular interaction should be equal. Okay. So what are the applications of this solubility of liquids and liquids? Complications of completely miscible liquid-liquid system, binary solution, right? That is a miscible liquid-liquid system. So first application in the formulation in the pharmaceutical dosage form in the pharmaceutical industry, right? So how we have to choose the right solvent to mix each other that form the binary solution. The second one is volatile liquid. Components of the binary solid mixture can be separated from other liquids and less volatile components by means of simple process name is called distillation. Through that we can separate the one liquid from another liquid where the volatility is different. Okay, these are the applications of liquids in liquids. Okay, the next one is partially miscible liquid-liquid system. I am adding this 50% of the liquid A and mixed with 50% of the liquid B. If I mix, that will be mixed but not completely mixed. Partially miscible, maybe 20 to 30% of the component A or component B mixed with component A. Okay, so a liquid-liquid system is said to be partially miscible when two components of the system get separated into two layers. Okay, it's not completely miscible. Then what will happen? Two layers we can get in the separation funnel or separating funnels. Okay, each layer containing some amount of the other liquid in dissolved in state. If I have the A and B, if it is coming under the miscible, that means partially miscible liquid state. Here this component partially dissolved in the bottom component, and this bottom component is partially miscible in the above component. Okay, so 10% is above component and the 10% above component should be available in the below component. So this is the partial miscible liquid system. Okay, they are miscible only in a fixed proportion. 10% of A dissolved in the component B, and the same way 10% of the B component B dissolved in this component A. Okay, at high temperature, most of the two liquid phases become a single liquid phase. While increasing the temperature, the partial miscibility will be disappeared and make a single layer. Two layers are there. Once you increase the temperature, that will become a equal layer. There is no kind of double layer. Only one layer will be appeared in the solution. Okay, so in a liquid phase, so that form a homogeneous solution. Initially it is a heterogeneous kind of component, then while increasing the temperature, it will make it as a homogeneous. That is, solubility is enhanced while increasing the temperature. At high temperature, where the miscibility occurs is called critical solution temperature. Where in which temperature the two layers become one layer is called as, or the particular temperature is called as critical solution temperature, CST. Okay, abbreviation. So example, we can say partially miscible liquid system. Phenol water system is the example. Okay, so another one is methanol cyclohexane. As I shown here this particular picture. In the left side is the completely component A, the right side is completely only the another component B. Okay, if I just take this side water, this side phenol, I'm keep on increasing the temperature from left to right. If I just increase the temperature, what will happen? This in particular stage, in the particular point, critical solution temperature, once it is reached, that two layers become single layer at the critical solution temperature. What is the critical solution temperature for phenol water system? That is 66.8 degrees C is the critical solution temperature for phenol water system. Okay, so here I just shown in this PPT the slide. Point A is 100% water, while moving to the left to right, the point B is the 11% of phenol. Okay, you can see the ratio. But if it is going to the right side, the point C is almost 63% phenol, and it is mixed each other after at the temperature of critical solution temperature. Okay, here phenol water system just shown again to you guys. So this is all combinations of phenol and water system, and above this temperature are completely miscible and yield one phase liquid system. That is the important concept in this critical solution temperature and liquids and the overall system. Okay, so what are the factors affecting the liquids and liquids, particularly partially miscible liquid system? Okay, example, phenol water system is the partially miscible liquid system. If I increase the temperature, what will happen? Yeah, it will make a single phase. That means all two liquids are completely miscible each other and form a single phase or single solution, and homogeneous solution will be reached, that will be attained. Next one is effect of foreign substances. If I add any kind of additional component or any salt or any foreign substances, any solid molecules in the partially miscible liquid system, it is increase in the mutual solubility of partially miscible systems by the addition of a foreign substance is referred as blending. What is blending? Increase in the mutual solubility, like temperature, this mutual solubility will be increased while adding the foreign substances is called as blending. Okay, addition of 0.1 molar naphthalene to phenol water system, it increases the critical solution temperature is 20 degree, while adding the KCl, 0.1 molar KCl, potassium chloride, the phenol water system critical solution temperature is increased or approximately to 88 degrees C. Okay. Okay, here immiscible liquid systems, carbon tetrachloride and water if you take. Okay, a liquid system is said to be immiscible each other when the components do not mix at all, then irrespective of their proportions. Whatever the proportions if you add, that won't miscible each other. This is the example I just shown the pictures how the two layers are separated each other, water and carbon tetrachloride. Okay. Okay, we'll go to the, so far we have gone through or discussed about two liquid systems. Okay, now we are going to discuss about ternary system. That means three liquids are existing in the one component, how the proportion is. Okay, so addition of third liquid to a pair, that means two component system, partially miscible, particularly partially miscible liquids produce a ternary system. We have the two liquid system, we are adding the third component, then it became a ternary system. Okay, any point within this triangle, the right side I shown the triangle, H is the one liquid, M is the another liquid, L is the another liquid, three component system, there is a ternary system. Okay, if you see the triangle, at any point within this triangle represent the overall composition of a ternary system at a fixed temperature and pressure. By conversion, the highest component L is located on the apex, that means top. The highest concentration of H is located on the left hand side. The highest concentration is located on the right hand side as M, right? So while the heavy and medium components are placed at the left hand corner and right corner. In the middle, the x-axis middle, if you see this, there is a component of H and M is mixed each other. If you see the y-axis, the H and L components are mixed each other. Almost you can see the center part, the H and L components are there, but there is no M component.